Now let us look at the very first and the classical example of using divide and conquer approach. Now this is a binary search. You might be familiar with this binary search. Let us assume that we have these elements, that there are 1, 2, 3, 4, 5, 6, 7 elements in the collection, and we have to find an element. Now very first thing, if you observe that these elements are in sorted order, and binary search works only when the elements are in sorted order. Now let's assume that these elements are stored in an array, and we can represent this array with the name as A. An array will have its indices, and here we are starting the index from 1 because this is the algorithms which we are seeing. We are not talking about any specific programming language. So if you use programming language, then obviously if you use C, C++ starts from 0. So, but this is an algorithm, so let us assume the array starts from 1 till 7. There are 7 elements. Now the solution for this binary search problem will be to compute the mid value and check or search for the element if it is present in the mid index. If it is present, return the mid index, or we will check if the element is searching element, the element which we are trying to search is less than the mid element. Then we will search for the left half of the array, and we will not bother about the right half of the array. That is where the divide approach is coming into. Divide and conquer approach strategy works. Then suppose if the search element is greater than the key element, or the search element is greater than the element at the mid index, then we try to search the right half of the array, and we are not bothered about the left half of the array. So that is where the divide and conquer approach comes. So this is the solution. We need to consider 3 points. Then let us first, before we go on to see any algorithm, we will look at how this works. Now let us see that we are trying to search for the key 48, or the search element is 48. Now we will compute the mid index. So to compute the mid index, we need to know the start index. That is, in this case, let us say L as the left index, which is the start index pointing to the, or referring to the first element. And let us try to take R index, which is the right index, which refers to the last element. Initially. So L initially is referring to the first element. R initially is referring to the last element. Remember, this is initial. Actually, L represents the left index, R represents the rightmost index. Now, to compute the mid value or the middle index will be floor of L plus R by 2. That is left index plus right index by 2. And then why we are using floor? Because the index or indices are always integer elements. And when we do something, when we divide something by 2, we may get a fraction or we may get a decimal point. So we take a floor value because we cannot have decimal as the indices. So here L initially will be 1, pointing 1, and R is pointing to 7, 7th index. So 7 plus 1 is 8. 8 divided by 2 is nothing but we get the result as 4. So mid will be pointing to index 4. Now is the element key, which is 48, we are trying to search, if key is equal to the element A of mid? Yes, it is true. So we found the element. Now this is actually the best case scenario, that the element is found at the mid index, the initial stage itself. Now let us look at another scenario. 34. Let us look at searching an element 34. Now we start with L pointing to the first index, R pointing to the 7th index, the last index. So L is 1, R is 7. mid value will be 1 plus 7 by 2, which is 8 by 2. Mid index will be 4. So mid will be pointing to 48. Now, is key, that is searching element 34, is equal to 48? No. Is it less? Yes, it is less than 48, the element at mid index. That is A of 4. So, this for 34, since it is less than 48, what we try to do is, we try to move the right index. If key is less than mid element, we try to move the right index to mid minus 1. We are not moving till mid minus 1. So, right index is moved to mid minus 1. When it is moved to mid minus 1, the rightmost part of the array is not considered now. So we are only left with the leftmost part of the array. Now, why we are saying r equal to mid minus 1? What we had is, we had this entire set of elements as problem P. Now we have divided this into two parts. Let's say P1 and P2, but P2 we are not considering. And we said that the sub-problems are non-overlapping. They do not overlap. So we cannot take r equal to till mid. If we take mid, then obviously you have already checked this mid value. So what is the purpose of checking again? So we don't take r till mid, we take it as mid minus 1. And same thing will be with respect to L also. Now, then L is 1 now, R is 3. So 1 plus 3, which is 4 by 2, which will be index 2. Now, mid will now be pointing. This mid will now be pointing to index 2. Again, we check whether 34 is equal to 21. It is not. Is it less than 21? No. It is greater than 21. So key 34 is greater than A of mid. So what we do is, we move L equal to mid plus 1. So even here, if you remember, if you observe, L is mid plus 1 not equal to mid, because they are non-overlapping. And mid we have already checked. So now what happens is, L moves to mid plus 1. So mid was 2. So L moved to 3. And then the left part of the array is now ignored, not checked again. Then L is 3, R will be 3. So 3 plus 3 is 6. 6 divided by 2 is 3. So mid index will be 3 now. So mid will be pointing to element at index 3. Now 34 is checked. It is equal. So the mid index is returned, and we say that we found the element at index 3. So this is how binary search works, by applying the divide and conquer approach. And dividing here is trying to divide the array into left half and right half, and try to search only in one part of the array. Now suppose, 69 will also work the same way. Let us suppose it's only going to search for the right half of the array. And let us try to search for some element 36. Obviously, if you look at this, it's not found, but let us look at how binary search works. So L is taken as the first index, R is taken as last index. So L will be 1, R will be 7. So 1 plus 7, 8. 8 by 2 is 4. So mid will be 4. Now then 36 is not equal to 48. 36 is less than 48. So R index is moved to the right. So R will be mid minus 1. Now L is 1. R is 3. So 1 plus 3 is 4. 4 by 2 is 2. So mid index is 2. Now 36 is not equal to 21. It is greater than 21. So L will move. L index will move. That is L equal to mid plus 1. Now once this is done, the first time we have ignored the right half of the array, then now we have ignored the left half of the remaining subproblem. Then again L will be 1, R will be 3. L is 3, R is also 3. And now L and R, L plus R, 6 by 2 will be 3 itself, so mid will also be pointing to 3. Now 36 is checked. If 36 is equal to 34, no, it's not equal to. 30 is 36 less than 34? No, it is greater than 34. So if it is greater than 34, L is moved to mid plus 1. Mid is 3. L will now be 3 plus 1, that is 4. So L will move to 4th index. Now here at this point, when L moves, so even this element 34 we have checked, we have examined that part of the array, and no more elements are now there in the array to be examined. We have examined all the elements, then no more elements to be examined. So how do we know there are no more elements to be examined? When the index L crosses the index R. So when L becomes greater than index R, that means we have examined, we have divided the array into half, 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 so and so. And when L crosses R, when L is greater than R index, that means we have examined all the elements of the array and the element we are trying to search is not found. So when L crosses R, we say that the element or whatever key we are trying to find is not present or not found in the collection of elements. So this is how binary search works. Now, formally a binary search is, the problem of the binary search is stated as, let AI be a list of n elements. AI means each one, where I is one between 1 to n. So there are n elements, I is 1 to n, A of 1 means 15, A of 2 means 21, and so, sorted in ascending order. This condition is very important. Sorted is ascending order. Otherwise, binary search will not work. Then the problem is to determine whether a given element X, whether the element X is present in the list or is present in the array. Solution would be, if X is present at A of j, that means A of j is equal to X, then we return the jth index, that is at this place it is found. That is what we are checking. A of mid equal to X, that is what we were checking. Now if X is less than the middle element or mid index, then search the left half of the array. Else, if X is greater than mid element, search the right half of the array. So this is how formally a binary search is defined. With the problem as well as its solution. Now, we said that binary search applies or uses divide and conquer approach. Now, divide and conquer approach has 3 things. First one is divide. 3 phases actually. So first phase is divide. Now here in this case, in binary search, dividing is nothing but examining the middle element. And based on the middle element, we divide it. If it's not found, key is not found, then we divide. Conquer approach is to search the left or the right half of the array. Search the left or the right half of the array and then get the solution. Now in this case, combining is trivial because we don't have any result that has to be combined. We just, if it is found, we just say we have the solution and then we just say we have the solution and then we give the result. That is, it is found or it is not found. So the 3 phases, that is divide, conquer and combine. 3 phases of divide and conquer for binary search is to examine the element. Divide part is to examine the element. Search part is to conquer. That is, conquer phase is to search. That is, search either the left or the right half of the array. And combining is trivial because it's not found. It's trivial because if it's found, we return the mid index. If it's not found, we just say not found. That's all. We don't pass on the result with add up to some other result or merge somewhere, do something. So combined part is trivial. Now binary search can be solved using 2 different ways. One is the iterative approach. The other one is the what we call as the recursive approach. Now, divide and conquer, I said that it uses recursive approach. That's fine. It uses recursive approach, no problem. But using iterations also, iterative approach also, iterative way also, we can perform divide and conquer and get the solution for the binary search problem. So let us consider this same array, and we will call this algorithm as bin search, which takes in parameter as a, which is the array, n as the number of elements, and key which we are trying to search. And the very first thing I told you, L has to be initialized at the first index initially, R has to be initialized at the last index, that is R equal to n. Then we will use a while loop to traverse the array, divide the array, and the condition is L less than equal to R. If L becomes greater than equal to R, that means L has crossed R index and there is no need to search the rest of the elements. So while L less than equal to R, we will compute the mid value, that is L plus R divided by 2. That is what we have seen. And suppose if the key is less than A of mid, then we will have R equal to mid minus 1. We will move R index to right, that is, if key is less than the mid element, that means it is going to be present, may be found in the left lower half of the array. It's less than, so obviously it's going to be in lower half. So we say R equal to mid minus 1. Else if the key is greater than mid, that means it's going to may be found in the upper half of the array. So we move the left index to mid plus 1 so that we only search the upper half of the array. Else, that means if key is less than, key is not less than, if key is not greater than, then key must be equal to the mid element. So if key is equal, else if key is equal to, we just return the mid index. Now here, either the while loop returns the mid index and we say it is found at so and so, a key is found at so and so index, or L becomes greater than R and this while loop terminates. When this while loop terminates, we return 0. That means it is key is not found. So this mid while loop returns a mid index or will terminate. If it terminates, it will return 0. Otherwise, it will return the mid index. So this is how iterative algorithm works for binary search. Now this while loop now let us look at the different the analysis for this algorithm, binary search algorithm. Now L is 1 and then R is the last index initially. Now this while loop will execute till L until L becomes greater than R. Now this inside the while loop we compute the mid index. Now let us say that for analyzing this, let us try to construct a graphical representation of what the mid values are. All the mid values, all possible mid values. So first thing we found is mid value is 4. So there is a node. Let us say that this is going to be a tree, which 4 is the node for the mid. Remember, it's not the element, it's the index, mid index. So if key is less than mid index, then what do? We move R. We are only considering the left half of the array. Then we again while loop executes and mid index is computed. So now mid index is 2. So on the left side, because this is 4 is divided, now mid index will be 2. Then again if key is less than 2, then what happens is R again becomes mid minus 1. So R moves to index 1 and now again mid index is computed for the while loop, and then we have mid index as 1. So here we are trying to compute or calculate all the possible mid indices that can be achieved here, or that can be found here. Then what about after 1? Is there any value remaining after 1, after mid index 1? No, there are no elements remaining. So let us make this as the orange node. Let us represent this as external node. So after 1 there is nothing, that means. Now what about before index 1? Are there any elements? We have darkened everything. This darkened everything means before 1 also there are no elements, because if if you consider this element 21, it is at mid index 2. Mid index 2, we already have this node for mid index 2. So that is why the right side of the 1 also doesn't have any elements. What this means is, suppose if the element is we are trying to find is 10. When the element we are trying to find is 10, obviously after at mid index 1 it's 15. So 10 means it should lie before 15. So are there any elements before 15? No. That means 10 is not found. So any element before 1, mid index 1, we are saying it's an external node. This external node represents the element not found. The same way, if we have an element 18. Now 18 is greater than mid but less than 21 in this case, so and mid is 1. So it has to be greater than 1 but less than mid index 2. So what is greater than 1, less than mid index 2? This node. This node. So this node is again an external node, we are saying, and we say if 18 is the element, we say it's not found. So that is why we are trying to construct a tree of all the possible mid values that can be computed for this collection of elements. Now let us move forward. From index 2, it was if it is greater than the key is greater than mid element, then obviously here we will have L equal to mid plus 1. So L moves over here, and then we will have, again we will compute the mid value. Mid value is 3. So we will be having a node 3 to the right of node 2. And node 3 is left as null. Sorry, not null. There are no elements to the left as well as right. So we get the external nodes here. Then what about the right side? So everything to the mid index, every mid index to the left of index 4 is computed. Now let us see what is there on the right side. We have on the right side the element we have mid L moves to the mid plus 1, and we have 6 as the mid index. So there will be a node created to the right of node 4. So which has mid index, possible mid index as 6. Then again, R moves if the key is less. So if the key is less than 6, then we have a mid index as 5. So we get the tree. The left child of mid index 6 is mid index 5. Then obviously for right of 5 and left of 5 there are no elements. And then if the key is greater than the mid, then L moves to mid plus 1. And now mid index will be computed, which will be 7 itself. So 7 becomes the mid index or the mid child of node 6. And there is nothing to the right and nothing to the left of 7 that needs to be compared. So this is how we create the entire structure or graphical representation, or we represent the entire computation of mid indexes using a binary tree. Now why this is considered as a binary tree or computed as a binary tree? Because every time we are dividing by 2, and looking at the left half or the right half at every stage. So that is why divide by 2. That is what is binary. 2 binary. Let us try to analyze. What will be the best case? The best case would be if the element is found at mid-index 4. That is at the first level itself, at the first computation itself, the element is found at the mid-index. That's the best case. So best case, since it is done at the first instance itself, and first instance means when L is computed, R is computed. We have a while loop. Obviously, while loop will run for O of n times. But this is a typical while loop. So when we enter the while loop, this while loop at the first instance itself at this mid place, it finds that the element key we are trying to search is equal to the mid index, and this is the best case. So while loop just returns the mid index at the first instance itself. While loop will not execute for n times or number of times. It only executes once. So we say best case is O of 1. Then let us compute the average of the worst case. Now, what would be the worst case of finding an element? Check mid index. If it is less, check again, then move to the next mid index, then move to the next mid index. So at the worst case would be trying to compare the element at the indices at every level. So there are 3 levels here. I mean, if you have large number of nodes, obviously the level of this tree increases. So the worst case is to search till the last, compare the element till the last level. So what is the last level? Last level is nothing but is the height of this binary tree, and height of the binary tree is log n. So when the height of the binary tree is log n, we say that at most log n comparisons we have to make. So the worst case of binary search is O of log n, because the log n is the height of the tree, and at most we have to make n number of log n number of searches, because till the last level we have to reach. Last level will be at height, that is the height of the tree, which will be log n. Now this is true for the worst case for successful as well as unsuccessful search. Even for unsuccessful search, that is nothing but the last level is all the external nodes which is represented by orange boxes. That is, element is not found at. So even for not element found or not found, we have to go to the last level in worst case. So in worst case, it is O of log n. Now, you may wonder that this is a while loop. While loop, it's a loop will run for n number of times. So instead of O of n, why is it becoming log n? Now this while loop is not going to run n number of times. If you have n number of elements, each time the size of the elements are reduced by half. Every time by half. So that is why you can see that the tree, initially if this is n, this will be n by 2, this will be n by 2. Then this will be n by 4, n by 4, n by 4, n by 4. So this keeps on going. Every time it is divided into half by half by half and by half. So that is why that series of this, at this level it is 1, at this level there are 2, this level there are 4, next level there will be 8 nodes. So this is a series, 2 power 0, 2 power 1, 2 power plus 2 power 2, plus 2 power 3, plus 2 power 4, so on till 2 power n. 2 power n is nothing but log n. So that series is nothing but log n series. So that is why this while loop will not run for n number of times, it will run for log n times. So in worst case, or even in average case, what we say is it's going to be O of log n times. So this is what is the time complexity with the binary search using iterative approach. In iterative approach, best case is O of 1, worst case and average case is O of log n. Now, there is another variation of the same binary search algorithm which is given in the textbook. it uses low index instead of L, it uses high index instead of R. This condition is same, low less than equal to high plus 1 is the condition, L less than equal to R. It's the same condition, it's no difference. Mid is computed same way, and then we check if it is less. If it is less, we make high. Am I audible?
Yes, sir.
Actually, I lost my internet connection, so I joined back again once this was restored. So anyway, I don't know at which place I lost the internet connection. So anyone can just give me a hint that because I was just talking, I was just giving the lecture. I don't know when that I was lost. The connection was lost. So just kindly give me a hint where I have. From where to continue? Anyone? While condition of which algorithm, man? Bin search one? Oh, other algorithm. Very good. Thank you. Thank you very much. Okay. Now, am I presenting? No. I did. Okay. Now here, this I suppose we were here. Okay. Anyway, this is the another iterative algorithm. So within the while loop, what happens is low and is less than equal to high minus 1. Now here remember that these two if statements, that is if I less than a of mid and I greater than a of mid is checked over here, greater than equal to actually. Now here high, that is R, and low, that is L. We are not using mid minus 1 and mid plus 1 because high itself we have taken to be n plus 1, just one more than the number of elements. So minus 1 and plus 1 is not needed here because high is one index more than the number of elements. Now this is actually a variation of the original algorithm itself. This is just for your information. Now what this is doing is, this while loop is not returning any values. This while loop executes till low is greater than mid. It executes till that time. And then we try to check if is x equal to low. If it is low, that means we found that element at that low index and we return that low index. And then else we return 0. So what it is doing is, if you observe in the previous algorithm, we were having 3 comparisons within the while loop. This algorithm just reduces one comparison, and that within the while loop. So what we say is, if there are 3 comparisons, one extra comparison, then the number of time while loop runs, those many number of times that extra comparison has to be performed. So instead of that, to make it a little more efficient, though the complexity will be of log n itself, but to make it little more efficient, one of the comparisons, which is whether it is found or not, equal to or not, is done outside the while loop. That is the only difference. But remember, for your exam or for your this one, for your any exam or any other evaluation purpose, this is the iterative algorithm you use. Don't use the bin search one iterative algorithm. Don't use this bin search iterative. This is only when a question is asked that how is iteratively a bin search performance can be improved, then only you have to go about this algorithm. Otherwise, the original algorithm the one which we have seen, and which is called as bin search, this algorithm is useful, or you have to use this algorithm. So this was about iterative part of recursive search. Binary search, iterative part of binary search. Now we will look at the recursive part, or recursive algorithm for binary search. Now obviously you all know L plus R. L is the left index, R is the right index. Let us call this binary as bin SRCH. You can use any name, it doesn't matter. Some places it's written as binary recursive or R binary search. It doesn't matter, you can use any name. So bin Array, what happened? Again, I suppose I lost the connection. Is it not? Just anyone reply? Okay, where was I? Where were we? Having a lot of problem with this, I don't know. Where was I?
You started recursive algorithm, sir.
Excuse me, sorry, I could not hear you.
Recursive algorithm you started.
Acha, okay. Let me do it once more. Okay. Now this recursive. Very first thing we will check. We lost the connection and I don't know where I was. So let me just repeat it once more. I don't know whether it is repetition or also. Anyway, we will look at this binary search algorithm. The first.
So you're not presenting the screen.
Okay. Screen is not. Oh, thank you very much. Sorry. Okay. Is it fine now?
Yes.
Okay. Thank you very much. Thank you. Now, let us look at this binary bin search once again. I'm just repeating it. It takes first parameter as A, which is the array. Second parameter is L, which is the left index. And initially left index will be 1. Then we have the third parameter as R index, which is the right index. Initially right index will be N, that is in this case 7. And the key, which is the element we are trying to search. Now here, this is a recursive. And we say that this uses divide and conquer strategy. So in divide and conquer strategy, in general algorithm, if you observe, we had if the problem is small. Now in this case binary search, the problem will be small when there is only one element left in the subarray. So when L is equal to R, that is when left index is equal to the right index, that means that there is only one element in the array and it is very easy for us to solve that problem. So when the problem is small, that means there is only one element in the subarray and we check if key is equal to that A of L, that element. Now here it can be A of L or A of R also, because they both are equal. If it is true, we return the L index or we can also return the R index. And if it is not true, that means element is not found. So this part of the F block is when the problem is small, when there is only one element in the array. Else, problem is large. We have to divide that problem. When we are dividing the problem, we use the same strategy, that is mid equal to L plus R divided by 2. Now, we have to either check whether the element is present at the mid index or not. Now, if it is present, That means here itself we have found the solution. And trying to divide the array itself, we found the solution and return the mid index. If the element x which we are trying to search, oh sorry, this should not be x, this should be key. This is key, sorry. This is key. What about here? Oh, here it is correct. Here it is problematic. Okay, no problem. Now, else if key is smaller than a of mid, that it is lies to the left side, then we recursively call the binary search algorithm. That is, this is bin search, passing a itself, that is the array, L index as it is, and instead of R index, we pass, you have seen in iterative, R equal to mid minus 1. So instead of R, we pass mid minus 1 here. Same strategy we are applying, same logic we are applying. Mid minus 1 and key will be as it is. If it is greater than, else means it's not equal, it's not less than, obviously it should be greater than. If it is greater than, then A is same, but instead of the left index, you might have, you remember L was equal to L plus, L equal to mid plus 1. So instead of L index, we pass mid plus 1 index, and R index remains same and key is passed. So this is how recursive binary search algorithm works, or this is how we write the recursive binary search algorithm. Now let us look at the time complexity of this algorithm. Let us look at the time complexity of this algorithm. Let us assume that bin search or binary search, recursive binary search, the time it takes is t of n. Assume that this is t of n is the time it takes. Now this part, if part, is when the problem is small. And this whole part only takes unit time to compute, because all statements are primitive statements. Unit time to compute. Then if the problem is large, we have the else part. In else part, mid is going to take, it's a primitive statement. If else returning mid value is a primitive statement, so they take unit of time. What about the else part? This else part will not recursively call binary search 2 times. It will not call binary search 2 times. The binary search recursively is called either on the left subarray or on the right subarray. It's not called 2 times. So this binary bin search, this return statement at line 14 is not going to take tn by 2, and return of bin search at line 16 is not going to take 2n by 2. If that happens, it will be 2tn by 2. But no. Either this is a conditional statement, else if, else. Either one of them will be called, not both at a time. Next time it is called, then either one of them will be called, not both at a time. So this entire thing is going to take t of n by 2, because only half tn is for binary search. So time taken by this will be t of n by 2, because we are only working on the half of the input every time. So the recurrence relation, if we look at the recurrence relation, if n is 1, that means this part. If n is 1 is this part. If L equal to R is this part. L is 1. If it is 1, it is taking unit time to compute. That is t of 1. This is 1. Else problem is large, that is n is greater than 1, then it's tn by 2 plus, obviously this is going to be, or whatever constant you add, this is going to be f of n, which is 1. So anyway, if you have any number of constant, doesn't matter. We can just ignore all those values and only take 1 as the constant. So this forms the recurrence relation for binary search algorithm. Remember, this is the recurrence relation for binary search algorithm. Now we have earlier also we have seen a recurrence relation. That was a general recurrence relation. This recurrence relation is specifically for binary search. And we got this recurrence relation through the steps from our algorithm, from our binary search algorithm. Now to find or analyze, find the time complexity, we have to solve this recurrence relation. Let us look at how to solve this recurrence relation. Now here, this is the recurrence relation what we have. Tn equal to 1 if n is 1, t of n by 2 plus 1 if n is greater than 1. Now remember, we can solve recurrence relation in two ways. One is using the substitution method, or it is also called as a successive substitution method. And another method is to use Master's theorem. Now, Master's theorem does not work on all or every recurrence relation. It works under certain constraints. So let us look at successive substitution method, or it is also called as substitution method, to solve this recurrence relation. Now, what is the first thing we have? Obviously, if n equal to 1, it is 1. So we are not bothered about that. We are bothered about how to solve if the value of n is large. So t of n from our recurrence relation, t of n equal to t of n by 2 plus 1. So this part, this forms the first equation. Let us consider this as the first equation. Now what we will do is, we will try to substitute in place of n. We will substitute n by 2, because on the next level the collection is divided into 2. So we will try to create an equation where n will be n by 2. So we will substitute in place of n, we will substitute n by 2. So this will be t of n by 2 equal to t of this n is n by 2 divided by 2, and plus 1 will be of the original equation itself. So here we have t of n by 2 equal to t of n by divided by 2 is 4. T of n by 4 plus 1. So this becomes our second equation. That is t of n by 2 equal to t of n by 4 plus 1. Then we will try to find another equation. Let us substitute in place of n. We substitute n by 2. We got the second equation. We will substitute n by 4. That is next level. If you look at the tree, next level, so first level will be n, second level it will be n by 2, third level will be n by 4. Each element will be n by 4. So what we will do is, we will substitute in place of n, we will substitute n by 4. So when we substitute n by 4, so this n is n by 4 plus t of n by 2 instead of n by 4 divided by 2. So this will be t of n by 4 equal to t of n by 8 plus 1. Plus 1 is from the original equation itself. So this becomes our third equation. Let us go a further one step further. Let us calculate fourth equation also, or the fourth level. So instead of we did it for n by 2, n by 4, we will do it for n by 8. So we will, instead of n, we will substitute n by 8. So it will be t of n by 8 equal to t of n by 8 by 2 is 16 plus 1. So this becomes our fourth equation. Now we will not go any further. We computed 4 equations just to have a clear understanding. Even 3 equations would have been sufficient. But to have clear understanding, we computed 4 equations. One with n, the other one with n by 2, third one with n by 4, and fourth one with n by 8. Now, we cannot go on further. Let us try to now use successive substitution method to get the answer. Now, look at here. T of n we have. You may, I mean, just follow the mouse pointer. We have T of n, which is equal to T of n by 2 plus 1. Now, in place of T of n by 2, we found the second equation. T of n by 2 plus T of n by 4 plus 1, second equation. So instead of T of n by 2, we will substitute the second equation, which is n by 4 plus 1. So it will be T of n by 4 plus 1 of this T of n by 2 plus 1 from the original equation. So this part is for T of n by 2. Then T of n by 4 can be substituted by the third equation. Third equation, here we have third equation. So T of n by 4 can be written as T of n by 8 plus 1 from the third equation, and then plus 1 is we have it over here, original equation. Then again from in place of T of n by 8, we can substitute T of n by 16 plus 1. So here T of n by 16 plus 1, this part is for T of n by 8, then plus 1 plus 1 plus 1, 3 times. Plus 1 plus 1 plus 1, we have it from the original equation. So this is 3 times we have successfully substituted the equation. That is T of n by 2, T of n by 4, T of n by 8. Now, we cannot go on further. If you go on further, doesn't matter. You have to create a fifth equation, substitute that equation. This doesn't, I mean, there's no point in continuing. Now, what we have to do now is this term, that is T of n by 2, n by 4, n by 8, n by 16. The rest of the other terms are all constant. So this has to be computed till when? Assume that it has to be computed till ith time. Till ith time. So if it is continued till ith time, what we get? First time is 2 power 0. Second time, actually this is the initial equation itself. First substitution we got, so this is 2 power 0. First substitution we got 2 power 1. Third substitution n by 2 power sorry. First part is 2 power 1. Second substitution 4 is n by 4 is n by 2 power 2. N by 8 is n by 2 power 3, third substitution. Fourth substitution is n by 2 power 4, which is 16. So this way, for the ith time, what we will have is n divided by 2 power I. That will be for the ith time. For the ith time, it will be n divided by 2 power I. Plus, now each time, first time 1, second substitution 2, 3, 4. So ith time it will be, so 1 I times. So 1 multiplied by I is nothing but plus I itself. So this equation, I mean, we got this equation for the ith time as T of n equal to T of n by 2 power I plus I. Now this T of, let us write it here, we use it here, T of n by 2 power I. Now what we have to do, what we say, is this problem we divide it such that we divide such that it reduces to a smallest problem. So what is the smallest problem? Smallest problem is when n is equal to 1. So when n equal to 1 means, if you look at this part, T of 1. T of 1 is 1. We know this 1. T of 1 is 1. We know it takes constant time. So when is T of 1? When n is 1. So this part should reduce. That is T of n by 2 power I should reduce to 1. So we can say that T of 1 means 2 power n by 2 power I is equal to 1. So when n by 2 power I becomes 1, we say it is T of 1 and T of 1 is 1 itself. We got the answer. So what will be n by 2 power I equal to 1? That will be equal to n equal to 2 power I. And that is nothing but I is equal to log of n base 2. N equal to 2 power I is I equal to log n base 2. So in this equation, t of n equal to, this becomes t of 1 plus I. Wherever I we have, we will substitute by log n. So we have, in place of I, we have substituted by log n. And t of 1, n is equal to 1. T of 1 is nothing but we have the answer as 1. When n equal to 1, it is 1. So t of n equal to 1 plus log of n, which is nothing but we can say that t of n, the function t of n, is O of log n. So in recursively, when we have computed its recurrence relation, and recurrence relation, we have applied substitution method, successive substitutions, we found the answer of t of n to be O of t of n to be 1 plus log n, that is the polynomial, which is nothing but we can say that it is O of log n to base 2 or O of log n itself. So both with iterative method as well as recursive method, the complexity of the or the time complexity of the binary search is O of log n. So this is how we compute the time complexity. So this was all about the binary search. We have seen how binary search works. We have seen how what is the iterative algorithm for binary search, and we have taken a tree of mid indexes and then evaluated the complexity of iterative binary search. We have looked at the recursive binary search algorithm, as well as we have, using the recurrence relation, we have computed the time complexity of the recursive binary search algorithm. Now, so this was all about binary search and its complexity and how it works and what is the how recursive algorithm recurrence relations compute. So each time when each algorithm we see, if it is a recursive algorithm, we will compute its recurrence. We will find its recurrence relation and then apply a substitution method to solve that recurrence relation and get the time complexity.